Hello everyone, my name is Stephanie and today I'll be talking to you about acid-base chemistry. At this point you probably have heard of acids and bases in some context, but you might not know exactly what it means for a chemical to be an acid or a base. We're going to start by talking about some learning objectives for the day. The following things are things that you should be able to do or understand by the end of this section. Understand definitions of acids and bases. Know which acids are strong acids and which bases are strong bases, and also the difference between strong and weak acids and bases. Third, we're going to be able to identify conjugate acid-base pairs, and we'll talk about what that means later. Fourth, we're going to understand the difference between mono, di, and triprotic acids. And last, we'll be able to predict what happens when acids and bases are mixed. So we're going to start by talking about the different definitions of acids and bases. And there are a few, and they're all named after the scientists who discovered them. So the first person to define what an acid or a base was in a technical way was this handsome gentleman, Svante Arrhenius. Before he talked about acids and bases, in 1884 he suggested that salts, like sodium chloride, which is table salt, dissociate when they dissolve in water. And the way that this works looks like this. Sodium chloride dissolves in water to give sodium plus and chloride minus. And he said that this is a dissociation reaction, and it gives you particles that he first called ions. So this is all information that you know. An ion is these positively and negatively charged particles. This doesn't have anything to do with acids and bases. But 3 years later, Arrhenius defined acids as neutral compounds that ionize when they dissolve in water, and they give you H plus ions. This is very similar to his previous definition, but this H plus positive ions seem to be special and have unique properties. So this was the first acid definition. And in this definition, HCl is an acid because it forms H plus and Cl minus in solution when it's dissolved in water. And H plus we'll refer to in a couple of different ways. Technically, it is protonated water, or H3O+, which we also call the hydronium ion. So if you add H plus to water, it becomes H3O+. But in solution, that essentially ends up being H plus, so we refer to it as H plus as well. So we can refer to it as hydronium, H3O+, H plus ion. We could also sometimes refer to it as a proton because it's a hydrogen atom without the electron. So you'll hear it called a couple of different things. I just want to be totally clear that all of them are the same thing. We're all referring to the same thing. Arrhenius also defined bases, and bases dissolved in water to give OH minus or hydroxide ions. So the way this looks here, it's sodium hydroxide. We dissolve it in water, and we get sodium plus and hydroxide minus. So an Arrhenius base gives you a positive ion and an hydroxide negative ion. This was all well and good, but later on in 1923, Johannes Bronsted and Thomas Lowry refined this Arrhenius definition to expand for more acids and bases that had been found to react a little bit differently. So in the Bronsted-Lowry definition, an acid is a molecule that donates H plus to another ion or molecule. So a Bronsted-Lowry acid is a species that donates H plus. So in this case, HCl is the acid because it's the H plus donor. And also in the Bronsted-Lowry definition, a base is a species that receives H plus. So in this case, water is the base because it receives H plus from HCl. So you can see that HCl is the H plus donor, and water is the H plus acceptor, so that's our acid base. And you can see that in the Bronsted-Lowry definition, in every exchange there is an acid and a base, no matter what. So this is a broader definition. So all Arrhenius acids and bases are also Bronsted-Lowry acids and bases, but not all Bronsted-Lowry acids and bases are Arrhenius acids and bases. So here's an example of that. You can see that nitric acid, or HNO3, donates a hydrogen to ammonia, or NH3. So you can see that hydrogen is donated, and we make ammonium ion, which is NH4+, and then NO3 minus doesn't have that hydrogen anymore. So you can see that HNO3 is a Bronsted-Lowry acid because it donates that hydrogen. Ammonia is a Bronsted-Lowry base because it accepts that hydrogen. but there's no H plus formed in the reaction and there's no OH minus formed in the reaction. So these are Bronsted-Lowry acids and bases, but they're not Arrhenius acids and bases. So this is, again, a broader definition, and it encompasses different species that the Arrhenius definition does not. So just to review these definitions of acids and bases, an Arrhenius acid is any substance that dissolves in water to give H+ ions. An Arrhenius base is any substance that dissolves in water to give OH- ions. A Bronsted acid is an H+ donor, and a Bronsted base is an H+ acceptor. And just so you know, from now on, we'll generally use the Bronsted-Lowry definition when we're talking about acids and bases. So you want to be thinking about acids as H+ donors and bases as H+ acceptors. So now we're moving on to learning objective 2, which is know which acids are strong acids, or the difference between strong and weak acids, and this applies to bases as well. So we know we can think of acids and bases as ionizing in water. We've seen that. But the extent of that ionization depends on the strength of the acid or base, and different acids are stronger or weaker than each other, the same for bases. So let's look at hydrochloric acid again. So we can see that HCl ionizes in water, and in the case of HCl, it's 100% ionized, and the ionization is irreversible. So because of that, HCl is considered a strong acid. All acids and bases that ionize 100% in an irreversible ionization are considered strong acids and bases. So this is a list of all the strong acids and bases. You should just keep this as a guide. You don't have to memorize it, and I'm not going to read them all out loud. When you see these acids and bases, you just need to know that this species will ionize 100% in water, and there's no going back. All other acids and bases are called weak acids and bases. And acetic acid, as shown here, is one. It ionizes in water, as you can see, to form CH3COO- anion and an H+, so same kind of interaction that you would expect. It donates H+. The ionization, however, is incomplete. It's much less than 100%. So the reverse acid-base reaction happens as well. So you can imagine that the H+ is donated, but it can kind of go back and forth. That's why you kind of see the equilibrium or the reversible arrows in this interaction. This is the case for all weak acids and bases. So moving on to learning objective 3, which is identifying conjugate acid-base pairs. So you kind of saw before that you can see this reversible interaction and this incomplete ionization. And you can see that CH3COOH and water then ionizes to CH3COO- and hydronium. In the forward direction, acetic acid, or CH3COOH, is the acid. It donates that H+ to water like we talked about in the Bronsted-Lowry definition. In the backward reaction, hydronium, or H3O+, is the acid. It donates that H+ back to CH3COO-. So you can see two different species acting as acids, and we want to designate them in a very clear way. So in the forward direction, we have acetic acid as the acid and water as the base. But in the backward direction, we consider H3O+ the conjugate acid, and CH3COO- the conjugate base. That's a designation that we make, and then we can label each member of the acid-base reaction. So in every acid-base reaction of this type, or ionization of this type, the acid becomes the conjugate base, and the base becomes the conjugate acid. That's how you can keep track of these designations. This is also true in reactions with weak bases. So you can see here, again, this exchange, we have ammonia and water. So in this case, ammonia is the base because it accepts a hydrogen from water, and NH4+, or ammonium, is the conjugate acid, and water is the acid because it donates that H+, and OH- is the conjugate base. That's how you would make a designation in a situation with a weak base. You can also make these designations with strong acids and bases. It's just that the reverse reaction will never ever happen, so it doesn't make as much sense. So moving on to learning objective 4, understand the difference between mono, di, and triprotic acids. Like we talked about earlier, the H plus ion that is donated in an acid-base reaction is often just referred to as a proton. And some acids have more than one proton that can be donated in an acid-base reaction, and these are called polyprotic acids. So poly means many or multiple, and protic means proton. So that just means that there are multiple protons in the acid that can be ionized. So as you might imagine, diprotic acids have two acidic protons. Sulfuric acid and H2S are an example. Triprotic acids have three acidic protons. H3PO4, H3ASO4 are two examples. And these acids ionize in separate steps. So you can see here with phosphoric acid, or H3PO4, we have three acidic protons. So we're going to ionize in multiple steps. We ionize with one H+, and we still have two hydrogens left on phosphoric acid that are acidic, so we keep going. We donate another hydrogen, and we have one acidic hydrogen still on HPO4 2-. And then finally, we donate the last hydrogen, and we have H+ and PO4 3-. No more hydrogens to donate, and so we know that this is done. So the way these polyprotic acids ionize is they just keep donating protons until there are no protons left to donate. So our final learning objective is learning objective 5, and we are going to be able to predict what happens when acids and bases are mixed. So we know that an acid and a water molecule results in a displacement reaction to form hydronium, or H3O+, and a negative ion. So here's HBr, and then we donate that hydrogen and we get H3O+ and Br-. We also know that a base in a water molecule results in a displacement reaction to form OH- and a positive ion. So here we have NaOH, we form OH- and Na+. So what happens when we add an acid and a base together? What happens is they end up neutralizing each other to make a water molecule and an ionic solid, which we call a salt. So here we have HBr and NaOH. You can see that when you donate that H+ to the base, it forms a water molecule, and what we have left over is sodium+ and Br-, which want to come together to make this ionic solid, or salt. So that's what we can expect when we add an acid and a base together. We always get water and an ionic solid. And salts are neutral, so the resulting solution is neither acidic nor basic. So this is actually pretty advantageous because, as you might know, acidic and basic solutions can be pretty corrosive and a little bit dangerous to deal with. So sometimes we want to neutralize those solutions, so we want to know what kinds of reagents to add to the solution in order to make it neutral. There are chemical compounds that we call indicators that can be used to tell you whether your solution is acidic, neutral, or basic. So depending on what you're trying to accomplish, whether you want an acidic solution, a neutral solution, or a basic solution, these chemical compounds can change colors in order to tell you where you're at and where you need to go. For example, if you have an acidic solution that you need to neutralize, you want to add base. And a lot of the time, stoichiometry is necessary in order to know how much base to add to get your solution neutral. This is just one example. You could also be going in other directions. So for example, say you have a 50 milliliter solution of 0.6 molar nitric acid. Now nitric acid is something that you do not want to deal with. It's really nasty and pretty corrosive. So you want to neutralize it. What you have is NaOH tablets at your disposal. Sodium hydroxide often comes in these little white tablets. And the molecular weight of sodium hydroxide is 40 grams per mole. So how are we going to figure out how many tablets or what weight of tablets we need in order to neutralize the solution and to make it safe to deal with? So the first thing you need to do is write a balanced equation. So if we're trying to neutralize this nitric acid, we want to add sodium hydroxide to nitric acid, and what we have is the displacement that we described earlier. We end up with NaNO3 and a water molecule. You'll see that it is balanced as written, and we don't have to do anything else to balance this equation. What we need to do is use stoichiometry to go from a 0.6 molar solution of nitric acid to grams of NaOH. So what do we have as far as information. We know that we have 50 mils of nitric acid, so we'll start there. We want to use molarity, and molarity is in moles per liter, so we want to get into liters. There's 1,000 milliliters in 1 liter, so in this case milliliters cancels out. The molarity is 0.6 moles per 1 liter, so liters of nitric acid cancels out. Now we want to go from moles of nitric acid to moles of sodium hydroxide. And we look at the balanced equation, and it's a 1-to-1 ratio, so we just have 1 mole of nitric acid, 1 mole of sodium hydroxide, and nitric acid cancels out. So now we want to go from moles of sodium hydroxide to grams, so we use the molecular weight. And if we do all that math straight through, we'll see that we need to add 1.2 grams of sodium hydroxide to our solution in order to make it neutral. So if we do that, we would neutralize our solution, and we'd be able to just dump it down the sink, and it would be very safe to deal with. So to review, there are 7 strong acids and 8 strong bases, and these react irreversibly to form H plus or OH minus. Every other acid and base is weak, and it reacts reversibly in equilibrium. The more H plus formed, the stronger the acid, or the more the equilibrium lies toward the products. And also this is reflected in a larger Ka or Kb value. And the product side of the reaction consists of the conjugate acid and conjugate base. And all acids have a conjugate base, and all bases have a conjugate acid. Polyprotic acids dissociate in multiple steps until there are no acidic protons left. And if you add an acid and base together, they neutralize each other, and they form water and a salt. You can use stoichiometry to figure out how much acid or base to use in order to make a solution neutral. So that's all that I have to say about acids and bases today. Hopefully you've learned a lot, and you can go back to those learning objectives at the beginning and see if there's anything that you're struggling with. If there is, you should review those slides, and if you still have questions, please let myself or your instructor know, and we can work with you. Looking forward to doing some in-class activities on this, and I will see you later.